In the autumn of 2025, something impossible passed within 18 million miles of Mars. A visitor from beyond our solar system, older than Earth, older than Jupiter, older than the Sun itself, moved through our cosmic neighborhood, defying 10 separate laws of physics. 10, not one unexplained behavior. Not 2 curious anomalies, but 10 simultaneous impossibilities documented by multiple space agencies, each one breaking patterns observed in thousands of comets over centuries of astronomy. What you're about to hear challenges everything we thought we understood about interstellar visitors. This isn't speculation from the fringes of science. This is data from NASA, the European Space Agency, and China's National Space Administration. The numbers are public, the calculations are verified, and they suggest that something passed through our solar system that doesn't fit into any natural category we've ever documented. On November 5, 2025, China released images captured by their Tianwen-1 Mars orbiter, the closest photographs ever taken of interstellar object, 3I Atlas. The comet had just lost 13% of its mass passing the Sun, 4 billion tons of material ejected into space. Physics demands this create a spectacular tail visible for millions of kilometers. Instead, the images showed only a fuzzy sphere. No tail, no debris field. Just silence where there should be chaos. How does 4 billion tons of matter disappear? And why did this ancient traveler born when the Milky Way was young choose a path that brought it past every major observation platform in our solar system while remaining perfectly hidden from Earth at its closest approach to the Sun? Tonight, we follow an object older than our world as it whispers through our solar system and vanishes back into the infinite dark. We'll examine the data that keeps astronomers awake. We'll explore what ancient civilizations might have known about cosmic visitors, and we'll ask the question that grows louder with each passing day. When something displays this many impossibilities simultaneously, at what point does highly improbable become intentionally designed? The universe has sent us a message. We have one chance to read it before it disappears forever. This is the story of 3I Atlas, the comet that wasn't quite a comet. In the mathematics of celestial mechanics, there exists a beautiful certainty. Objects follow predictable paths. Gravity doesn't negotiate. Light doesn't compromise. For 4 centuries since Newton first described universal gravitation, we've relied on this cosmic clockwork to navigate our understanding of the heavens. And then something breaks the pattern. October 3, 2025. While most of Earth turned its attention elsewhere, a spacecraft orbiting Mars tracked something that shouldn't exist according to our models: the Tianwen-1 probe. China's first successful Mars mission had been circling the red planet since February 2021. Its primary objectives were complete. The lander and rover Zhurong had surveyed Utopia. Planitia analyzed Martian soil, searched for water ice beneath the surface, but the orbiter remained, patient, watching. On this particular morning, Tianwen-1 turned its high-resolution camera away from Mars. Away from the russet plains and ancient river valleys it had photographed thousands of times. Instead, it pointed into the deeper darkness of space toward a target 18 million miles distant. Think about that challenge for a moment. The high-resolution imaging camera aboard Tianwen-1 was designed to photograph bright planetary surfaces from low-orbit mountains, canyons, dust storms reflecting sunlight. Now it needed to capture something fundamentally different, an object smaller than Manhattan, darker than asphalt, moving at 58 kilometers per second through the void. That's 129,000 miles per hour. At that velocity, you could circumnavigate Earth in 18 minutes. You could travel from New York to Tokyo in 90 seconds. The object was also approximately 10,000 times dimmer than the Martian surface. Some estimates suggested 100,000 times dimmer. Photographing it was like trying to capture a candle flame from 1,000 miles away, while that flame moves faster than any bullet ever fired. The China National Space Administration didn't announce they were attempting this observation. There was no press conference, no advance warning. They simply pointed the camera, calculated the trajectory, compensated for the relative motion, and captured a sequence of images over 30 seconds. When the data transmitted back to Earth processed through the ground application systems, the result was both historic and haunting. Black and white frames, a fuzzy sphere at the center surrounded by a diffuse glow, the coma, stretching several thousand kilometers across. The object itself barely resolved a blur of light against the stellar background. And nothing else. No tail streaming behind it, no fountain of debris, no spectacular display of matter ejecting into space. Just a quiet sphere of light moving through the darkness like a ghost ship sailing between stars. The CNSA called it an important technical achievement in their official statement. A test of their deep space imaging capabilities, preparation for future missions to asteroids and comets. All of this was true, but it was also perhaps the most significant understatement in recent astronomical history, because what Tianwen-1 captured wasn't just remarkable for what it showed. It was extraordinary for what it didn't show. Let me explain why the absence of a tail matters. Why this seemingly simple observation, a sphere without streaming debris, represents something that challenges our understanding of cometary physics. When a comet approaches the sun, it heats up. Frozen volatiles locked in the nucleus for potentially billions of years suddenly vaporize. Water ice becomes steam. Carbon dioxide ice becomes gas. Methane, ammonia. Cyanide compounds, all of them transition from solid to gas in minutes or hours. This isn't a gentle process. It's violent. The gas erupts from the surface with enough force to lift dust particles, rocks, fragments of the nucleus itself. Solar radiation pressure and the solar wind, that constant stream of charged particles flowing outward from the sun, push this material away, creating the iconic tail that makes comets recognizable. The closer the approach to the sun, the more dramatic the outgassing, the more spectacular the tail. 3I Atlas passed perihelion on October 30th, 2025. Perihelion, the closest point to the sun in its orbit. The distance 0.9 astronomical units. 1 astronomical unit is the distance from Earth to the sun, approximately 93 million miles. So 3I Atlas came within 84 million miles of our star. That's closer than Earth. At certain points in its orbit, closer than Venus. At that distance, the solar radiation is intense. The temperature on the nucleus would have soared from the frigid cold of interstellar space, perhaps negative 270 degrees Celsius, to potentially hundreds of degrees above zero on the sunlit side. NASA's Jet Propulsion Laboratory detected something extraordinary in the trajectory data: non-gravitational acceleration. This is a technical term that means exactly what it sounds like. The comet was accelerating in a way that couldn't be explained by gravity alone. Something was pushing it. The measurements are precise. At 1 astronomical unit from the sun, 3I Atlas experienced acceleration pushing directly away from the sun. There was also a component perpendicular to the sun's direction. Now, non-gravitational acceleration isn't unusual for comets. It's actually expected. The outgassing creates thrust like a natural rocket engine. As material jets off the surface, it pushes the comet in the opposite direction. This is how we've explained the orbits of dozens of comets whose paths deviated slightly from pure gravitational predictions. What makes 3I Atlas unusual is the magnitude of this acceleration combined with what we observe, or rather, don't observe when we look at it. Using momentum conservation, one of the most fundamental principles in physics, researchers calculated how much mass the comet must have lost to produce the observed acceleration. The answer: at least 13% of its total mass. The comet's estimated mass is approximately 30 billion tons. 13% of that is roughly 4 billion tons. 4 billion tons of material ejected into space over the course of a few days as it rounded the sun. To put that in perspective, if you could somehow collect all that material and compress it into a sphere, it would be roughly a kilometer across. A mountain's worth of matter cast off from the nucleus and pushed outward by solar radiation. 4 billion tons creates a visible tail. It has to. The physics is straightforward, tested across thousands of observations. When that much material leaves a comet, some of it gets pushed behind by radiation pressure, creating a visible stream that can extend for millions of kilometers. Comet Neowise, which passed perihelion in July 2020, ejected far less material than 3I Atlas. Its tail was visible to the naked eye from Earth, stretching across the night sky like a brushstroke of light. Comet Hale-Bopp in 1997 produced multiple tails, a dust tail and a gas tail that extended for hundreds of millions of kilometers, visible in evening and morning skies for months. These are the patterns. These are the rules written by physics, confirmed by observation, trusted by astronomers for generations. 3I Atlas broke them. The images from Tianwen-1 captured just 4 days after perihelion show a compact coma. A fuzzy sphere, the anti-solar direction where the tail should be pointing directly away from the sun, is visible in the frame. Empty. Ground-based telescopes confirmed this. The Virtual Telescope Project in Italy photographed 3I Atlas on November 5th. The R-Naves Observatory in Spain captured it the same day. Both facilities are equipped with sensitive instruments capable of detecting faint structures. Both showed the same thing, a sphere of light with no obvious tail. For comparison, the same R-Naves Observatory photographed Comet Leonard just 2 days earlier on November 3rd. Leonard displayed a clear, well-defined tail pointing precisely away from the sun, exactly as expected. It looked like what a comet should look like. 3I Atlas did not. Now, before we descend deeper into the mystery, let's acknowledge the conventional explanations. Let's be fair to the natural hypotheses, because science advances through careful consideration, not through jumping to dramatic conclusions. Maybe the viewing geometry is wrong. Maybe we're looking at the tail edge on, seeing it from an angle that makes it appear foreshortened or invisible. Like looking at a pencil from the point end, you see a dot, not a long object. This is possible. Cometary tails don't always extend in a perfect straight line. They can curve, fan out, orient themselves in complex ways depending on the solar wind conditions and the comet's rotation. But 3I Atlas was observed from multiple locations. Earth-based telescopes from different hemispheres. Mars orbiters at a completely different vantage point. The European Space Agency's Mars Express and Trace Gas Orbiter also photographed it during its close approach to Mars. Different perspectives, different angles, all showing the same absence of a prominent tail. Maybe the ejected material was primarily gas, not dust. Gas tails are often harder to see because individual molecules don't reflect light as efficiently as dust particles. Maybe 3I Atlas lost 4 billion tons of pure gas, which dissipated quickly and became invisible. This is also possible. Comets do produce gas tails that can be difficult to detect visually, though they're often visible in specific wavelengths, ultraviolet light, for instance, where certain molecules emit strongly. But spectroscopic observations of 3I Atlas did detect compounds in the coma: carbon dioxide, cyanide molecules, some water vapor, though less than expected. These observations confirm outgassing occurred. The question is if outgassing was violent enough to eject 13% of the mass-producing measurable acceleration. Why isn't there more visible structure? Why no streaming patterns, no fountain-like ejections, no asymmetry in the coma shape that would indicate active jets? Maybe the mass loss calculations are wrong. Maybe non-gravitational acceleration was caused by something other than outgassing. Though this opens its own set of questions, because what else could push a comet that isn't gravity or reaction thrust from escaping gas? These explanations exist. They're being investigated by researchers who prefer natural conventional answers, and rightly so. Science should always exhaust the ordinary before embracing the extraordinary. But here's the uncomfortable truth that lingers in the data like a whisper in an empty room. When you need multiple special circumstances to explain a single observation, when you have to stack unusual conditions on top of rare geometry, on top of atypical composition, that's when the alarm bells start ringing in the back of a scientist's mind. Because 3I Atlas isn't just anomalous in this one way. The missing tail is anomaly number 10. There are 9 others. There's something deeply humbling about encountering an object older than your world. We live on a planet that formed 4.54 billion years ago, give or take a few million years. Our sun ignited about 4.6 billion years ago, condensing from a cloud of gas and dust in the Orion spur of the Milky Way. Everything in our solar system, every planet, every moon, every asteroid and comet shares roughly the same birthday. We're all children of the same stellar nursery siblings born from the same cosmic cloud. But 3I Atlas doesn't belong to this family. Scientists analyzing its composition and trajectory believe it formed somewhere between 3 and 11 billion years ago. Let that settle in your mind for a moment. 11 billion years ago, the universe itself was only 2.8 billion years old. The first galaxies were still forming. The Milky Way was a chaotic, violent place, stars colliding, merging, exploding. Massive stars lived fast and died young, seeding space with heavy elements forged in their cores. And somewhere in that ancient chaos in a star system we will never identify around a sun that may no longer exist. 3E Atlas formed. It has traveled. Oh, how it has traveled. If we assume it's 8 billion years old, splitting the difference of the estimated range, then it has been wandering the galaxy since before complex life arose on Earth. Since before animals. Since before plants. Since before oxygen filled our atmosphere, turning our skies blue. This object was already ancient when the first cells divided in Earth's primordial oceans. It witnessed, if an unconscious mass of rock and ice can witness the birth and death of countless stars. It drifted through nebulae, those vast clouds where new stars kindle into existence. It passed binary systems, triple systems, maybe even black holes, always moving, always alone, always silent. 4 billion tons of this ancient traveler's mass sublimated away when it passed our sun. 4 billion tons of matter that formed in another era, in another corner of the galaxy, under conditions we can only guess at. That material is gone now, dispersed into space, lost. But what remains continues its journey. And that journey is taking it away from us, back into the darkness, back into the spaces between stars, where it will continue for perhaps another billion years, until something gravity collision entropy finally ends its voyage. The discovery itself was almost accidental. The way so many great discoveries are. July 1st, 2025. The Atlas Survey Telescope in Chile Atlas stands for Asteroid Terrestrial Impact. Last alert system designed to spot potentially hazardous objects near Earth detected a faint point of light moving through the constellation Sagittarius. At first, nothing seemed unusual. The telescope detects thousands of objects. Most are asteroids. Some are comets. Occasionally they spot something interesting enough to warrant follow-up observations. But within a week, as more data accumulated, astronomers began calculating the object's orbit. And that's when everything changed. The orbit was hyperbolic. In celestial mechanics, orbits come in several shapes.
Elliptical orbits are closed loops. The object comes around again and again, bound by gravity to whatever it's orbiting. Planets orbit the sun in ellipses. Moons orbit planets in ellipses. This is the geometry of belonging. Hyperbolic orbits are open curves. The object comes and swings around and leaves. Forever. It's not bound. It's just passing through a visitor that arrived from elsewhere and will depart to elsewhere, never to return. 3I Atlas follows a hyperbolic trajectory. The object is moving too fast to be captured by the sun's gravity. It's an escape trajectory, but hyperbolic orbits around the sun aren't necessarily proof of interstellar origin. Sometimes comets or asteroids from the outer solar system get gravitational assists from planets Jupiter, Saturn that accelerate them onto escape paths. They're still solar system natives, just flung outward. The decisive evidence came from the trajectory's orientation and velocity.
3I Atlas came from outside the solar system at a velocity of approximately 30 kilometers per second relative to the local standard of rest. That's the average motion of stars in our neighborhood of the galaxy. That velocity is too high to be explained by any gravitational interaction within our solar system. It came from interstellar space. That much became clear quickly. What took longer to understand was just how anomalous its path was. Most objects in our solar system orbit close to the ecliptic plane, that flat disk where the planets live. This makes sense for anything born here. We all formed from the same rotating disk of material, so we all inherited that rotational motion. But interstellar objects arrive from random directions. There's no preferred orientation. The galaxy isn't a flat disk on the scale of individual stellar systems. Stars and their planets are oriented every which way.
So, when an interstellar visitor arrives, it should come from any angle, up, down, sideways, diagonal. There's absolutely no reason for it to align with our ecliptic plane. 3 Atlas aligns to within 5 degrees. 5 degrees is essentially flat relative to the planetary plane. It's like throwing a stone from a mile away and having it skim perfectly horizontal across the surface of a pond. The probability of this happening by chance, 0.2%. 1 in 500. Not impossible, but unlikely enough to make astronomers take notice, and that's just the first anomaly, the first of 10. When the Minor Planet Center officially designated it 3I Atlas in August 2025, it joined a very short list. Only 2 other confirmed interstellar objects had ever been detected. I Oumuamua in 2017 and 2I Borisov in 2019. 3 objects. 3 visitors from other star systems, and each one more puzzling than the last. Oumuamua remains the most controversial. It was small, perhaps 200 meters long and 35 meters wide, shaped like a cigar or a pancake, depending on which rotation model you believed. It tumbled through space in a complex rotation that didn't match known asteroids or comets. And it accelerated without visible outgassing, a behavior that still lacks a satisfying natural explanation. Some researchers suggested it was a hydrogen iceberg outgassing invisible hydrogen as it heated. Others proposed it was a nitrogen ice fragment from a Pluto-like world evaporating without leaving traces. Still others, most notably Harvard astronomer Avi Loeb, argued that the acceleration was consistent with a light sail. A large, thin, reflective surface pushed by solar radiation. A light sail, artificial, constructed. The suggestion was met with skepticism, sometimes bordering on hostility from the mainstream astronomical community. Oumuamua was a natural object, they insisted. Unusual, yes, but natural. Then came 2I Borisov in 2019. This one looked more conventional, an actual comet with a visible tail outgassing as expected. Its composition showed high concentrations of carbon monoxide, higher than most solar system comets, but otherwise it behaved according to established models. For a moment, the astronomical community relaxed. See, interstellar objects are just comets and asteroids ejected from other systems. Nothing mysterious, nothing requiring exotic explanations. And then 3I Atlas arrived, bigger than both previous visitors. Much bigger, with a nucleus estimated between 5 and 6 kilometers across and a mass of approximately 30 billion tons, it dwarfs Oumuamua by a factor of 1,000,000. Moving faster, too. Its velocity through the solar system exceeded both previous interstellar objects by a significant margin, and displaying behaviors that defy comfortable categorization. The size and speed combination alone is statistically troubling.
Larger objects are rarer than smaller ones. This is true throughout the galaxy. Faster objects require more energy to eject from their parent systems, so they're also rarer. The probability of detecting an interstellar object that is both exceptionally large and exceptionally fast, less than 0.1%. 1 in 1,000. We've detected 3 interstellar objects total. The third one happens to be 1,000 times more massive and moving faster than the others. Coincidence? Perhaps, or perhaps our sample size is still too small to make meaningful statistical claims. 3 objects is barely a pattern. It's 3 data points in an infinite cosmos. But here's what makes 3I Atlas particularly intriguing from a historical perspective: its age. If it's truly 8 to 11 billion years old, as compositional analysis suggests, then it formed during an era of the Milky Way that was fundamentally different from today. 11 billion years ago, the galaxy was metal-rich, metal being an astronomer's term for any element heavier than helium. The first generations of stars had already lived and died, exploding as supernovae and seeding space with carbon, nitrogen, oxygen, iron, nickel, all the elements that make planets and life possible. Star formation rates were higher then. The galaxy was more active, more violent, more chaotic, and planetary systems were forming everywhere. Some of those planets may have developed life, maybe even intelligent life. The universe is 13.8 billion years old after all. Earth is only 4.5 billion years old. There was plenty of time for other civilizations to arise, flourish, and perhaps even die out long before our sun ignited. Could 3I Atlas have formed in a system that hosted life-intelligent observers who watched their own skies and wondered about their place in the cosmos? We'll never know. But the object itself carries information. Its chemical composition is a fingerprint of its birthplace. The ratios of elements, the isotopes present, the minerals in its structure, all of these tell a story about where it formed and under what conditions. And that story, as we're discovering, is deeply strange. Let me tell you about a pattern ancient astronomers would have recognized immediately. In the cosmologies of Egypt, Sumeria, China, and Mesoamerica, celestial objects that moved against the background of stars were considered significant. Planets. The word comes from Greek planets, meaning wanderer, were tracked meticulously because their movements seemed purposeful, geometric, predictable, yet complex. They didn't just drift randomly, they followed paths, patterns, as if guided. The Babylonians kept astronomical records spanning centuries, noting the positions of Jupiter and Venus with such precision that modern computers can verify their observations. The Maya calculated the synodic period of Venus, the time it takes to return to the same position relative to the Sun, to within minutes of the actual value. Why? Because predictable movement suggested intention, order, meaning. Objects that moved in perfectly aligned geometric patterns were considered messages from the gods, or, in some interpretations, the gods themselves. Now we no longer attribute celestial mechanics to divine intervention. We understand gravity. We can calculate orbits with extraordinary precision. We know the sun's mass curves space-time, and objects follow geodesics through that curvature. There's no mystery anymore, except when something arrives from interstellar space and its trajectory aligns perfectly with our planetary plane, despite having no reason to do so. 3I Atlas entered our solar system from the direction of Sagittarius, traveling retrograde, opposite to the orbital direction of the planets, but doing so almost precisely within the ecliptic plane, 2 within 5 degrees. Imagine standing in a vast three-dimensional space, a sphere extending in all directions. Now imagine the ecliptic plane as a thin disk cutting through that sphere like the brim of a hat or the rings of Saturn. An object arriving from interstellar space could come from any direction within that sphere. Up, down, diagonal, there are infinite possible approach angles. The ecliptic disk represents less than 0.2% of the total solid angle around the Sun. So when an interstellar object arrives and its trajectory lies within that tiny slice of three-dimensional space, that's interesting. Not impossible, just interesting. 1 in 500 statistically speaking. But it gets stranger. The trajectory didn't just align with the ecliptic plane in orientation. It also brought 3I Atlas past multiple planetary observation platforms in sequence, almost like a scheduled tour. First, Venus. The comet passed within tens of millions of kilometers in September 2025. Not close enough to be significantly affected by Venus's gravity, but close enough for detailed spectroscopic observation from spacecraft. Then Mars. The approach distance in early October was approximately 30 million kilometers, again close enough for the European Space Agency's Mars Express and Trace gas orbiter to photograph it. Close enough for Tianwen-1 to capture the closest images ever taken of an interstellar object. Then it swung past Jupiter. Again, not a super close approach, but within observable range. Each encounter happened when spacecraft were present and operational. Each encounter allowed different types of observations, spectroscopy, imaging, photometry. And here's the detail that makes this particularly curious. The timing of perihelion. The closest approach to the Sun occurred on October 30th. At that moment, 3I Atlas was directly between Earth and the Sun. Directly. This meant that at the moment when the comet was presumably at its brightest, experiencing maximum solar heating, potentially displaying its most spectacular outgassing activity, it was completely unobservable from our planet. The Sun blocked our view. Ground-based telescopes, which represent the majority of observational resources available to astronomy, were useless. Hundreds of facilities around the world, equipped with instruments far more powerful than anything we can put in space, couldn't see it. Only spacecraft positioned away from Earth. Mars orbiters, Venus orbiters, space telescopes at different orbital positions could observe perihelion. The probability of this timing occurring by chance, 0.005%. 5 in 100,000. Now let's be clear about what this means and what it doesn't mean. It doesn't mean 3I Atlas deliberately planned its route. Comets don't have engines. They don't navigate. They follow ballistic trajectories determined by gravity and initial velocity. But it does mean that of all the possible trajectories through our solar system, millions of potential paths, each one equally probable from a random distribution. 3I Atlas followed one that aligned with the ecliptic plane, passed near multiple planets in sequence, and timed perihelion to occur when Earth couldn't observe it directly. Any one of these would be moderately unusual. All three together multiply the probabilities into very small numbers. And when probabilities become sufficiently small, you have to ask, are we witnessing a statistical fluke, or is there something about this object's origin or nature that makes this trajectory less random than it appears? Harvard astrophysicist Avi Loeb has made this point repeatedly in his analyses. He's not claiming divine intervention or alien spacecraft. He's making a statistical argument. When you see patterns this precise, you should at least consider whether there's a non-random component to explain them. In his papers, Analyzing 3I Atlas, Loeb calculates what he calls probability, cascades a method for assessing how likely it is for multiple independent anomalies to occur simultaneously in the same object. Start with the base assumption: interstellar objects are natural randomly ejected from other star systems following random trajectories. Now add evidence: the ecliptic alignment, the planetary encounters, the perihelion timing. Each piece of evidence slightly shifts the probability landscape, not proves anything, just changes the likelihood ratios. After 10 pieces of evidence, 10 separate anomalies. The cumulative probability that all of them are random coincidences becomes vanishingly small, less than 1 in 10,000, possibly less than 1 in 100,000. At what point does highly unlikely become implausible? At what point does the cautious scientist trained to always prefer natural explanations have to acknowledge that maybe the natural explanation isn't sufficient? These are uncomfortable questions. They push against centuries of scientific training that emphasizes skepticism of extraordinary claims. But they're also honest questions asked in good faith based on actual data. And they're questions that ancient astronomers, lacking our mathematical formalism but possessing their own sophisticated understanding of celestial patterns, might have recognized instantly. When an object moves through the heavens in ways that seem too perfect, too aligned, too precisely timed, that's when you pay attention. The Babylonians would have recorded this. They would have noted the dates, the positions relative to familiar constellations, the brightness changes. The Maya would have incorporated it into their long count calendar, calculating when such an event might recur. The Egyptians might have built something to mark it, a shaft aligned to the trajectory, a temple oriented to commemorate the passage. We don't build temples anymore. We build spreadsheets and run simulations. But the fundamental question remains the same. When the cosmos presents a pattern too precise to ignore, what does it mean? Is it teaching us about physics we don't yet understand, some mechanism that preferentially ejects objects into ecliptic aligned trajectories? Is it revealing selection biases in our observations? Maybe we only detect interstellar objects that pass close to planets because those are the ones that get bright enough or close enough to notice. Or is it hinting at something else entirely, a non-random component to this object's trajectory that suggests purpose rather than accident? We don't know yet. But the alignment remains. Documented, measured, undeniable. And the trajectory carries 3i Atlas away from us now, back into the darkness, taking its secrets with it. By December 19, 2025, it will pass approximately 270 million kilometers from Earth, roughly 700 times the distance to the Moon. That will be our last good opportunity to observe it. After that, it fades beyond the reach of even our most powerful telescopes. By January 2026, it exits the solar system completely, and whatever answers it might have provided, whatever resolution to the mystery of its perfect alignment, will be gone, lost, traveling at 200,000 kilometers per hour into the spaces between stars where no human instrument will ever see it again. The ancient astronomers understood something we sometimes forget in our era of precise measurements and computer models. Celestial events are often unrepeatable. A comet appears once, displays its wonders, and vanishes. If you miss it forever. August 15, 1977. Ohio State University's Big Ear Radio Telescope was conducting its regular survey of the sky, listening for signals from space. The telescope couldn't move, it was a fixed structure, and the rotation of Earth swept its field of view across the heavens like a slow searchlight. At 23:16 Eastern Time, it detected something extraordinary, a narrowband signal, extremely strong, lasting 72 seconds. The signal peaked at a frequency of 1420 megahertz, the emission line of neutral hydrogen, the most abundant element in the universe. This frequency is significant because any civilization capable of radio astronomy would know about it. It's a natural beacon, a cosmic standard that intelligent beings might use to signal their presence. The astronomer reviewing the computer printout the next day was so surprised by the signal's intensity and characteristics that he circled it in red pen and wrote a single word in the margin: "Wow." The wow signal, as it became known, has never been satisfactorily explained. It didn't repeat. Follow-up observations of the same region of sky detected nothing. The signal appeared once for 72 seconds and then fell silent forever. Its source appeared to come from the direction of Sagittarius, somewhere near the constellation's border with other star groups. The exact location was never precisely determined. The Big Ear's design limited positional accuracy, but the general direction was clear. Now here's where it gets strange. In July 2025, when astronomers first detected 3I Atlas and began calculating its trajectory, they traced it back through space, following the path it must have traveled to arrive in our solar system. The object came from the direction of Sagittarius, to within 9 degrees of the WOW signal's origin. 9 degrees is a relatively small patch of sky, about 18 times the width of the full moon. In cosmic terms, for an object that has traveled potentially thousands of light years, it's remarkably close to the only unexplained artificial-looking radio signal we've ever detected. Is this meaningful? The honest answer is probably not. Sagittarius covers a large area of the sky. It's also in the direction of the galactic center, meaning when we look toward Sagittarius, we're looking toward the densest concentration of stars in the Milky Way. Statistically, more stars means more planetary systems, which means more opportunities for objects to be ejected into interstellar space. So it's not surprising that an interstellar object would come from that general direction. And 9 degrees, while small in absolute terms, is still large enough that the alignment could be coincidental. The probability of this alignment occurring by chance, approximately 0.6%. 1 in 167, not definitive, not even particularly compelling by itself. But when you add it to the list of other anomalies, the ecliptic alignment, the planetary encounters, the perihelion timing, the pattern becomes harder to dismiss because each anomaly taken individually has a conventional explanation. But all of them together appearing in the same object strain the limits of coincidence. Ancient civilizations were particularly attuned to Sagittarius. The Sumerians associated it with Nergal, god of war and the underworld, but also with knowledge and secrets. The constellation represented a gateway, a doorway to mysteries beyond human understanding. In Sumerian astronomy, objects appearing in Sagittarius were omens. Comets, especially. The clay tablets from ancient Mesopotamia contain detailed records of celestial events, including descriptions of hairy stars that appeared near the gateway of the gods. Were they seeing the same kinds of interstellar visitors we're detecting now? We'll never know. The tablets don't contain enough detail to determine whether the objects they recorded were solar system comets or interstellar intruders. But the reverence with which they treated these appearances suggests they understood these were unusual events worthy of preservation. The WOW signal itself sparked decades of speculation. What was it? Natural phenomenon? Interference? Or something else? The signal's characteristics were consistent with an artificial transmission. The frequency, the intensity, the duration, the narrowband nature, all of these pointed toward technology rather than natural cosmic processes. But without repetition, without confirmation, it remained an unsolved mystery. One data point. Intriguing, but not conclusive. And now, 48 years later, an object arrives from approximately the same direction. An object that displays 10 separate anomalies. An object that loses 4 billion tons of mass but shows no tail. An object older than our solar system carrying a chemical composition unlike anything we've seen before. Is there a connection? This is speculation, but consider the following thought experiment. Suppose a civilization billions of years ago wanted to send something through the galaxy. Not a message encoded in radio waves that would dissipate and weaken over distance. Not a spacecraft that would require millennia of travel time and constant energy, but something simpler, something durable, a physical object, dense. Designed to survive the journey through interstellar space for billions of years, equipped with materials that would remain stable across cosmic timescales. And suppose as this object approached other star systems, it needed a way to announce its presence. Not continuously broadcasting that would waste energy and might not be noticed by civilizations in their early radio astronomy phase, but perhaps a single brief transmission, a pulse, strong enough to be unmistakable if anyone happens to be listening. brief enough that by the time observers point their telescopes at the source, it's gone, creating a mystery that would be remembered and discussed. A signal in 1977, an arrival in 2025. The timing gap is right for an object traveling at 30 kilometers per second across the intervening distance. Now, is this what actually happened? Almost certainly not. The WOW signal's explanation is likely far more mundane, a reflection off space debris perhaps, or an atmospheric phenomenon we didn't understand in 1977. And 3I Atlas's origin from the same general direction is probably coincidental. But the fact that we can even construct this narrative, the fact that the data allows for this interpretation, however unlikely, tells us something important about where we are in our understanding of interstellar objects. We're still in the pattern recognition phase. We're seeing things we can't explain and trying to fit them into frameworks we understand. And sometimes those frameworks don't quite fit. The ancient astronomers didn't have our mathematics. They didn't have radio telescopes or space probes. But they had something we're at risk of losing in our data-driven age: the ability to see patterns and ask questions without immediately needing definitive answers. When the Sumerians saw omens in the sky, they weren't being superstitious. They were acknowledging that the universe contains events beyond their current understanding, and those events might be significant. The WOW signal was an omen in exactly that sense. An unexplained event, a cosmic question mark, and now 3I Atlas, another unexplained event, another question mark. Maybe they're connected. Maybe they're not, but asking the question, being willing to consider the possibility, that's what keeps science honest. Because the moment we stop asking uncomfortable questions, the moment we insist that everything must fit into existing frameworks, we stop discovering. And 3I Atlas, whatever it is, whatever it represents, is nothing if not a discovery that refuses to fit. In medieval alchemy, there was a concept called the philosopher's stone, a substance that could transmute base metals into gold, cure diseases, perhaps even grant immortality. The alchemists never found it, of course. Transmutation turned out to require nuclear reactions, not mystical substances. But the deeper idea behind the philosopher's stone wasn't really about making gold. It was about transformation, about substances that shouldn't exist according to the rules of the material world, about finding something that breaks the patterns and forces you to reconsider what's possible. 3I Atlas is an alchemical substance, not because it transmutes elements, but because its chemical composition breaks the rules in ways that force us to reconsider what we thought we knew about comets and their formation. When spectroscopic analysis of the coma began in July and August 2025, astronomers expected to see the typical signatures of a comet water vapor: carbon monoxide, carbon dioxide, perhaps some methane and ammonia. Simple molecules frozen since the object's formation, now vaporizing as solar heat warmed the nucleus. What they found instead was deeply unusual. First, the water content approximately 4% by mass. 4%. To put that in perspective, typical comets are 70 to 80% water ice. They're dirty snowballs, mostly frozen water with some rock and dust mixed in. Water is the primary component because comets form in the cold outer regions of planetary systems where water freezes readily. 3I Atlas contains 96% non-water material. That makes it more like an asteroid than a comet. Asteroids are rocky or metallic objects formed in the warmer inner regions of planetary systems where water doesn't condense as easily. They're dense, hard, durable. But 3I Atlas shows cometary activity, outgassing a coma non-gravitational acceleration. It's behaving like a comet despite not having the composition of one. How does something with only 4% water produce enough outgassing to lose 13% of its total mass and create measurable acceleration? That question leads to the second anomaly, the metallic composition. Spectroscopic observations detected strong emission lines from nickel. Nickel. Not just traces, not minor amounts, but concentrations high enough that the nickel-to-iron ratio was inverted compared to natural comets. In every comet ever observed, if metals are present at all, iron dominates.
The iron-to-nickel ratio in cosmic materials typically ranges from 10:1 to 20:1, reflecting the abundances of these elements in the universe. 3I Atlas shows more nickel than iron. This ratio is characteristic of industrial nickel alloys materials we manufacture on Earth, specifically because nickel's properties make it useful for high-stress, high-temperature applications. Spacecraft construction, for instance, rocket engines, heat shields. Now, before jumping to conclusions, let's acknowledge that unusual metal ratios can occur naturally in certain environments. Some asteroids show elevated nickel concentrations due to differentiation processes when a molten body separates into layers based on density, creating a nickel-rich core. But 3I Atlas isn't showing asteroid-like behavior in other ways. It's outgassing, it has a coma, it's accelerating non-gravitationally, it's behaving like a comet with the composition of a nickel-rich asteroid. There's no known formation mechanism that produces this combination, and it gets stranger. The ratio of nickel to cyanide detected in the coma was orders of magnitude higher than any known comet, including 2I Borisov, the previous interstellar comet. Orders of magnitude means factors of 10, 100, possibly 1,000. This isn't a slight variation, this is a completely different chemical fingerprint. Cyanide, specifically the molecule CN, is common in comets. It forms in cold, carbon-rich environments and gets trapped in ice during comet formation. When comets approach the Sun, cyanide sublimates, along with water and other volatiles, creating a distinctive spectral signature. The fact that 3I Atlas has such high nickel relative to cyanide suggests either 1. It formed in an environment with vastly different chemical conditions than anything in our solar system, perhaps around a star with unusual abundances of heavy elements, perhaps in the remnants of a supernova that seeded its surroundings with freshly synthesized metals. Or 2. The nickel isn't primordial, it's not from the object's formation, it's something else. Something added later. The probability of a natural comet displaying this composition below 1%. Now let's explore what this might mean through the lens of history and alchemy. The alchemists believed in correspondence, the idea that earthly materials reflected cosmic principles. Gold was associated with the sun because of its color and incorruptibility, silver with the moon, iron with Mars, copper with Venus. These weren't arbitrary associations, they reflected deeper patterns the alchemists observed in nature. Nickel was discovered relatively late in human history, 1751 by Swedish chemist Axel Fredrik Cronstedt. Before that, it was often mistaken for copper ore, but wouldn't yield copper when smelted. Miners called it kupfernickel, Old Nick's copper, devil's copper because it seemed cursed. The name stuck. Nickel. Nick. Associated with trickery with things that aren't what they appear to be. How fitting that an object from interstellar space, displaying anomaly after anomaly, contains unusually high concentrations of the element named after deception. But beyond the linguistic coincidence, there's a deeper question. Why nickel if 3I Atlas were simply a natural comet with an unusual formation history, we'd expect it to show a suite of chemical anomalies reflecting that unusual environment. Elevated levels of multiple elements, odd isotopic ratios across various compounds, a whole pattern of deviations from the norm. Instead, we see specifically elevated nickel, one element. Precisely the element that would be useful for constructing something designed to survive billions of years in interstellar space. Nickel alloys are corrosion resistant. They maintain structural integrity across wide temperature ranges. They're used in environments where durability is paramount. Is this meaningful? Is the nickel concentration telling us something about the object's nature?
Or are we seeing patterns where none exist, like medieval alchemists convinced that lead could become gold if only they found the right formula? The difference is that we have data, real measurements, spectroscopic observations, confirmed by multiple independent teams. 3i Atlas contains more nickel than iron, far more nickel relative to cyanide than any natural comet, and only 4% water despite showing active outgassing. These are facts, not speculation. What those facts mean, that's where interpretation comes in, and here's what makes interpretation difficult. We have only 3 interstellar objects to compare. Oumuamua's composition was never directly measured. It passed through our solar system before we could obtain detailed spectroscopy. We know it accelerated anomalously and had an unusual shape, but its chemical makeup remains unknown. 2i Borisov looked more conventionally cometary with high carbon monoxide concentrations, but otherwise familiar characteristics. It was different from solar system comets, but recognizably similar, and now 3i Atlas displaying a composition that doesn't fit either pattern. Sample size of 3, each one different, each one strange in its own way. We can't yet say what's typical for interstellar objects because we don't have enough examples. But we can say what's typical for solar system comets. We've observed thousands of them over centuries. And 3i Atlas doesn't match that pattern. It's an alchemical substance, in the truest sense, something that forces us to reconsider the rules. The medieval alchemists were wrong about transmutation, but right about the deeper principle. The universe contains substances and processes that don't fit into tidy categories. Things that challenge our frameworks and demand new understanding. 3i Atlas is one of those things. Whether it's revealing new physics, new chemistry, new formation mechanisms, or something stranger remains to be seen. But its composition is documented, measured, real, and deeply, profoundly unusual. There's a kind of magic trick called the vanishing lady. A magician brings a woman on stage, has her step into a cabinet, closes the door, and then opens it to reveal she's disappeared. The audience gasps. Where did she go? The answer, of course, is misdirection. Secret panels, mirrors, trapdoors. The lady never actually vanished. She just went somewhere the audience couldn't see. But here's the thing about cosmic magic: there are no trapdoors in space, no mirrors, no hidden compartments. When 4 billion tons of matter leaves a comet and then seems to disappear, physics demands an explanation. Let's review what we know.
NASA's Jet Propulsion Laboratory analyzed the trajectory of 3i Atlas as it passed through the inner solar system. They measured its position over time with extraordinary precision, tracking deviations from the path pure gravity would prescribe. They detected non-gravitational acceleration forces pushing the comet that couldn't be explained by the sun's or planet's gravity. The acceleration had 2 components. One pushing directly away from the sun, the radial component. One perpendicular to that direction, the transverse component. This is exactly what we expect when a comet outgasses. Material jets off the sun-facing side, creating thrust like a natural rocket engine. The comet gets pushed in the opposite direction. Using the measured acceleration values and applying conservation of momentum, researchers calculated how much mass must have been ejected to produce those forces. The answer: approximately 13% of the object's total mass. With an estimated mass of 30 billion tons, that's roughly 4 billion tons of material. 4 billion tons. To give you a sense of scale, if you took Mount Fuji, Japan's iconic volcano, and lifted it entirely off Earth's surface, it would weigh about 3 billion tons. So we're talking about more than an entire mountain's worth of matter ejected from this comet in the span of a few days as it rounded the sun. Now, when a comet ejects that much material, it doesn't just vanish. Physics prohibits that. Mass is conserved. The material has to go somewhere. Solar radiation pressure and the solar wind push ejected gas and dust away from the sun, creating the characteristic tail. The
The tail is visible because dust particles reflect sunlight and gas molecules emit light at specific wavelengths when excited by solar ultraviolet radiation. The more material ejected, the brighter and more extensive the tail. Comet Hale-Bopp, which graced our skies in 1997, had a tail that extended more than 100 million kilometers, roughly the distance from Earth to the Sun. Its nucleus was estimated at about 60 kilometers across, and it ejected material continuously for months as it passed through the inner solar system. 3I Atlas is much smaller, only about 6 kilometers across, but it ejected a significant fraction of its mass in a very short time. That should create a dramatic visible tail, perhaps not as long as Hale-Bopp's, but certainly detectable. The Tianwen-1 images from October 7th, just 4 days after closest approach to Mars, and 1 week after perihelion, show a compact coma extending a few thousand kilometers from the nucleus. No extensive tail. Ground-based observations from the Virtual Telescope project in Italy and the R-Naves Observatory in Spain, taken on November 5th, 6 days after perihelion, confirm this. Both facilities photographed 3I Atlas using sensitive equipment capable of detecting faint structures. Both showed the same thing, a fuzzy sphere with no obvious tail extending into the anti-solar direction. For comparison, the R-Naves Observatory photographed Comet Leonard on November 3rd, just 2 days earlier. Leonard displayed a clear, well-defined tail pointing precisely away from the Sun, exactly as cometary physics predicts. So where did 3I Atlas's 4 billion tons go? Let's examine the conventional explanations. Hypothesis 1: Viewing geometry. Maybe we're looking at the tail from the wrong angle. Maybe it's pointed toward or away from Earth, foreshortened by perspective, making it appear much shorter than it actually is. This is possible. If the tail were aligned with our line of sight, we'd see it as a diffuse glow around the nucleus rather than an extended structure. But 3I Atlas was observed from multiple vantage points. Earth-based telescopes from different hemispheres. Mars orbiters at 90-degree different perspectives. The European Space Agency's Mars Express and Trace Gas Orbiter also photographed it. All showed similar results: compact coma, no extensive tail. For the viewing geometry explanation to work, the tail would have to be oriented such that it appeared foreshortened from all these different perspectives simultaneously. That's geometrically unlikely. Hypothesis 2: Pure gas. Ejection. Maybe the 4 billion tons were mostly gas rather than dust. Gas tails are harder to see because individual molecules don't reflect sunlight as efficiently as dust grains. Carbon dioxide gas, for instance, is nearly invisible in optical wavelengths. If 3I Atlas ejected primarily CO2, the outgassing might not produce a visible tail despite the large mass loss. But spectroscopic observations did detect emissions from the coma. Cyanide molecules, some water vapor, carbon dioxide. These observations confirm that at least some of the ejected material was present and detectable. Moreover, pure gas ejection would create a Type 1 gas tail pushed directly away from the Sun by the solar wind at speeds much faster than dust. These tails are often visible in ultraviolet or blue wavelengths because molecules like CN fluoresce under solar ultraviolet radiation. Observations didn't show a prominent gas tail either. Hypothesis 3: Rapid dispersion. Maybe the ejected material dispersed so quickly that it became undetectably diffuse within days. In principle, gas molecules moving at high velocities could spread out quickly enough that their density dropped below detectable thresholds. But 4 billion tons is a lot of material. Even if it dispersed rapidly, there should be some detectable structure asymmetry in the coma, for instance, or faint extensions in the anti-solar direction. The observations show remarkable symmetry. The coma appears roughly spherical without obvious streaming features that would indicate where the ejected material went. Hypothesis 4: Fragmentation. Maybe the outgassing was so violent that the nucleus partially fragmented, ejecting large chunks rather than fine dust and gas. Large fragments would follow ballistic trajectories rather than being pushed by radiation pressure. They'd separate from the parent comet and become individual objects potentially too faint to detect unless you were specifically looking for them. This is plausible. Comets do fragment sometimes. Comet Shoemaker-Levy 9 famously broke into more than 20 pieces before colliding with Jupiter in 1994. But fragmentation events are typically detectable. The fragments create their own mini-comas as they heat up. Tracking systems spot them as they diverge from the parent body's trajectory. No fragments from 3I Atlas were reported. Observers were watching it closely, and a fragmentation event involving 4 billion tons of material would have been newsworthy. So we're left with a mystery. The physics clearly indicates massive mass loss. The acceleration is measured, the forces are calculated, the momentum conservation is straightforward. 4 billion tons left that comet. But the observational evidence shows no corresponding tail, no debris field, no obvious destination for that material. It's as if the mass simply vanished. Now, matter doesn't vanish. That would violate some of the most fundamental laws of physics, so either our mass loss calculation is wrong, our observations are missing something, or something about 3I Atlas's behavior doesn't match conventional cometary models.
Here's where speculation begins, but let's be clear about labeling it as such, speculative scenario. What if the outgassing wasn't random? What if material was ejected in a directed way? Not spraying in all directions like a typical comet, but focused, controlled. Imagine a series of jets oriented such that the ejected material was directed primarily toward or away from Earth, making it difficult to detect from our perspective. Or imagine material ejected in a tight beam narrow enough that unless you were looking at exactly the right angle, you'd miss it entirely. This would require a level of organization and structure we don't typically associate with natural comets. But it would explain the observation's massive mass loss without a visible tail. Is this likely? Probably not. Is it impossible? No, and that's what makes 3I Atlas so fascinating. It occupies that uncomfortable space where the conventional explanations feel incomplete, but the unconventional explanations feel too exotic. The vanishing lady trick works because the magician controls the situation. Every detail is planned. The cabinet is constructed specifically to enable the illusion. 3I Atlas isn't performing a trick, it's just following physics, but somehow physics has produced a result that looks very much like magic. 4 billion tons of matter that left a comet and then seemed to disappear. The ancient alchemists would have called this transmutation, the transformation of one thing into another in ways that seem impossible. Modern science calls it an anomaly, a deviation from expected patterns that requires explanation. But both perspectives share a common thread, the recognition that sometimes nature does things we don't understand, and those moments of incomprehension are opportunities to learn something new. 3I Atlas's ghost mass. The 4 billion tons that vanished is teaching us something. We just haven't figured out what yet. There's an Egyptian myth about Ra, the sun god, traveling through the underworld at night. In this journey, Ra's solar boat moves against the current of the celestial river. The waters flow one direction, but Ra must go the opposite way, battling demons and chaos to reach dawn. The myth represents the impossible motion against natural flow. Water doesn't run uphill. Rivers don't reverse course. And yet Ra's boat does exactly that, powered by divine will rather than natural law. In July and August 2025, 3I Atlas did something that shouldn't happen according to cometary physics. It shot material toward the sun, not away from it, toward it. Multiple observatories documented this. A jet of material extending from the nucleus in the sunward direction, the opposite of every pattern we've observed in thousands of comets. Let me explain why this is significant. When a comet approaches the sun, solar radiation heats its surface. Frozen volatiles, water, carbon dioxide, methane vaporize, erupting from the nucleus as gas.
This gas carries dust particles with it, creating jets that can be quite directional depending on the comet's rotation and the location of active areas on the surface. But regardless of which direction the jets initially point, when they leave the nucleus, solar radiation pressure acts on the ejected material. Photons, particles of light, carry momentum. When they hit dust grains or gas molecules, they transfer that momentum, pushing the particles away from the sun. This is how cometary tails form. The solar wind, a stream of charged particles flowing outward from the sun, also pushes ionized gas away. Between radiation pressure and solar wind, cometary material always ends up moving anti-sunward. Away from the star. Always. The force is relentless and unavoidable. Trying to move material sunward against radiation pressure is like trying to swim up a waterfall. Physics simply doesn't allow it, and yet 3I Atlas appeared to be doing exactly that. The sunward jet was observed in late July and early August, when the comet was still far from perihelion, but close enough that solar heating had begun triggering outgassing. Astronomers analyzing the images initially thought it might be an optical illusion. There's a phenomenon called an anti-tail, where viewing geometry makes a comet appear to have a spike pointing toward the sun. But it's not real material, it's just our perspective seeing a curved tail edge-on, like looking at a boomerang from the wrong angle. Anti-tails are well understood. Astronomers know how to identify them. You check the viewing geometry, calculate the expected projection, and verify whether the apparent sunward extension matches what you'd see from a regular tail viewed from that angle. Multiple teams ran these calculations for 3I Atlas. The sunward jet didn't match anti-tail geometry. It was actual material extending from the nucleus toward the sun, visible in multiple wavelengths, confirmed by several independent observatories. How there's no conventional explanation, no known mechanism that allows cometary material to move sunward against radiation pressure, unless the material isn't being pushed by outgassing alone, unless there's another force involved. Hypothesis. What if the sunward jet wasn't material falling back onto the nucleus, though that's also impossible against outgassing pressure, but rather material being actively propelled, not by natural outgassing but by something else, something that could generate thrust in a controlled direction, overwhelming the radiation pressure that should push everything away from the sun? This is speculation, but it's speculation forced by observation. We saw something that shouldn't happen. Either our understanding of cometary physics is incomplete, or this object is doing something that natural comets don't do. Ancient mythologies are full of stories about celestial objects that move against the expected order. The Egyptian myth of Ra's reverse journey. The Greek myth of Phaethon, who drove the sun's chariot erratically across the sky. The Mayan beliefs about Venus as a warrior planet that broke celestial rules. These myths weren't just stories. They were attempts to explain observations that didn't fit normal patterns. When ancient astronomers saw comets or planets that seemed to behave strangely, retrograde motion, unexpected brightness, changes, unusual trajectories, they recorded these as significant events. Omens, messages, because motion against the expected flow suggested intention, purpose, something beyond random natural processes. Now we don't interpret astronomical anomalies as divine omens anymore. We look for physical mechanisms, natural explanations. But the underlying principle remains. When something moves in ways that seem to violate natural law, it demands attention and explanation. The sunward jet from 3I Atlas lasted several weeks before dissipating. By mid-August, it was no longer visible. Whether it stopped because the outgassing pattern changed, because the comet's rotation altered, which areas were active, or because whatever was causing it simply turned off, we don't know. What we do know is that for a period in July and August 2025, this object produced a jet of material pointing toward the sun, defying the radiation pressure and solar wind that should have pushed it the other way. That's documented, observed, real. the explanation for why it happened that's still missing. And without an explanation, we're left with an Egyptian boat sailing up the celestial river, moving against the current through mechanisms we don't understand, powered by something that might be natural but doesn't look like anything we've seen before. In the autumn of 1811, a brilliant comet appeared in Earth's skies. The Great Comet of 1811, as it became known, was visible to the naked eye for months, sporting a magnificent tail that stretched across constellations. That comet's appearance coincided with excellent wine harvests across Europe, leading to the vintage being called comet wine. People believed the comet had somehow influenced the grapes, though the connection was pure superstition. But the comet also inspired wonder and careful observation. Astronomers noted its color, yellowish-white like most comets, reflecting the sun's own color as sunlight bounced off dust in the coma and tail. This is normal. Comets should appear roughly the same color as the sun because they're primarily reflecting solar illumination. Sometimes they look slightly redder if their dust contains iron-rich materials, or slightly greener if molecular emissions dominate. But fundamentally, comets are mirrors showing us the sun's light bounced back. 3i Atlas turned blue, not slightly blue, not ambiguously blue, but distinctly, measurably, significantly blue. A preliminary analysis published in late October 2025 found that the comet appears distinctly bluer than the sun. This wasn't a casual observation, it was spectrophotometric analysis measuring the exact wavelengths and intensities of light coming from the object. Blue light has shorter wavelengths than red light. When something appears bluer than its illumination source, it means shorter wavelengths are being preferentially reflected or emitted, while longer wavelengths are being absorbed or scattered away. In nature, blue colors typically come from one of two mechanisms. First, Rayleigh scattering. This is why Earth's sky is blue. Molecules in the atmosphere scatter shorter wavelengths more efficiently than longer ones, so sunlight gets scattered, and we see blue. But Rayleigh scattering works on particles much smaller than the wavelength of light molecules, tiny dust grains. It doesn't work well on the larger dust particles, typically found in cometary comae. Second, fluorescence, or emission. Certain molecules absorb ultraviolet light from the sun and re-emit it at visible wavelengths, including blue. Cyanide molecules, for instance, fluoresce in the blue part of the spectrum. 3i Atlas does contain cyanide that was detected spectroscopically, so maybe the blue color comes from CN fluorescence. But here's the problem. The blue color appeared when the comet underwent its unprecedented brightening near perihelion. The rate of brightening didn't match any cometary models. Comets brighten as they approach the sun because heating increases outgassing, which increases the amount of dust and gas in the coma, which increases the surface area reflecting sunlight. This brightening is predictable. We have equations relating heliocentric distance to brightness for thousands of comets. 3i Atlas brightened much faster than those equations predicted. Not slightly faster, dramatically faster, and it did so while turning blue. So we have two linked anomalies, unexpected rapid brightening, combined with an unusual color change, both happening simultaneously as the comet approached perihelion. What could cause this? Hypothesis 1. A sudden increase in highly reflective dust ejection. Maybe the perihelion heating triggered an outburst, a sudden violent release of material from beneath the surface. Outbursts happen. Comets can brighten by factors of 10 or more in hours if a subsurface pocket of volatiles suddenly vents. But this doesn't explain the blue color.
More dust should make the comet more reflective across all wavelengths. Not selectively blue. Hypothesis 2, fragmentation. Exposing fresh, pristine ice that reflects more efficiently than the weathered surface. Fresh ice can be brighter and bluer than the yellowish, dust-contaminated ice on a comet's surface. Possible, but again, we'd expect to see evidence of fragmentation, multiple pieces expanding debris clouds. None were reported. Hypothesis 3, fluorescence from unusual molecules. Maybe 3I Atlas contains compounds we haven't detected before, molecules that fluoresce strongly in blue wavelengths when excited by solar ultraviolet radiation. This is more plausible. The object's unusual composition, high nickel low water, suggests its chemistry is different from normal comets. Perhaps it contains molecules that don't exist in our solar system's comets.
But what molecules? And why would they suddenly activate at perihelion? Or, and this is speculation, what if the blue light wasn't reflected or fluoresced sunlight at all? What if it was emitted? There are processes that can produce blue light directly. Cherenkov radiation, for instance, the eerie blue glow produced when charged particles move through a medium faster than light, travels in that medium. This happens in nuclear reactors and is distinctly, unmistakably blue. But Cherenkov radiation requires specific conditions, a transparent medium and high-energy particles moving through it. Neither seems applicable to a comet's dusty gaseous coma. Still, the fact that we can even consider emission mechanisms, that we're looking at a brightening event that doesn't fit reflection models, suggests something unusual was happening. Ancient civilizations associated blue celestial phenomena with special significance. The Egyptians venerated blue as the color of the night sky of the primordial waters of creation. Blue faience, a glazed ceramic material, was used in amulets and religious objects, specifically because its color mimicked divine realms. The Maya associated blue with sacrifice and rain, vital forces that sustained life. When they painted murals or created ceremonial objects, blue pigment was reserved for the most sacred contexts. And across many cultures, blue stars, rare anomalies, were seen as portents, messages from beyond the normal order. 3I Atlas didn't just turn blue. It brightened while turning blue, violating the brightness models derived from thousands of observations, displaying a color that doesn't match conventional cometary processes. Was this a natural outburst of exotic materials or something else we don't know? What we do know is that for a brief period near perihelion, this ancient object from interstellar space shone with a blue light that shouldn't exist in a normal comet's repertoire. And then, as it moved away from the sun, the blue faded. By the time Tianwen-1 photographed it on October 7th, and by the time ground-based telescopes captured it in early November, the color had returned to more normal tones. The blue fire had burned out, leaving only questions. There's a fossil in the British Museum that never fails to move me. It's an ammonite, a spiral-shelled marine creature from the Jurassic period, about 170 million years old. Looking at it, you're seeing an individual animal that lived, swam through ancient seas, hunted, maybe reproduced, and then died. Its shell settled into sediment, was buried, mineralized, and preserved across unimaginable spans of time. That fossil is a message from deep time. It tells us about environments that no longer exist, about life forms that vanished, about an Earth radically different from today's. 3I Atlas is also a fossil, not biological but geological, a frozen remnant from an era of the galaxy we can barely imagine. When we analyze its composition and calculate its age, we're reading a message written billions of years ago. The estimated age, between 3 and 11 billion years, comes from several lines of evidence. Isotopic ratios in the detected compounds, the degree of space weathering inferred from its surface properties, dynamical modeling of how long it might have been wandering interstellar space based on its velocity and trajectory. These methods are imperfect. We're making inferences from limited data, but they all point toward extraordinary age. If 3I Atlas is 11 billion years old, then it formed just 2.8 billion years after the Big Bang. Think about what the universe was like then. The first generation of stars, massive pure hydrogen and helium, had already lived and died, exploding as supernovae and seeding space with heavy elements: carbon, oxygen, nitrogen, iron. All the elements that make planets and life possible were newly abundant. The Milky Way was still assembling. Smaller galaxies were merging, creating the spiral structure we see today. Star formation rates were much higher. The galaxy was brighter, more active, filled with stellar nurseries where new suns ignited by the thousands. And planetary systems were forming everywhere. Around metal-rich stars, second or third generation stars made from the debris of earlier supernovae planets, condensed from protoplanetary disks, rocky worlds in the inner regions, gas giants farther out, and in the cold outer zones beyond the frost line, comets formed from ice and dust. 3I Atlas might have formed in one of these systems. Around a star we'll never identify orbiting in the Kuiper Belt equivalent of some long-lost planetary system accumulating ice and dust for millions of years, until gravitational perturbations, maybe from a passing star, maybe from a giant planet's migration, flung it into interstellar space. And then it wandered. For billions of years it drifted through the galaxy, moving at speeds determined by its ejection velocity and subsequent gravitational encounters. It passed through different regions of the Milky Way regions that have changed dramatically over cosmic time. When 3I Atlas began its journey, intelligent life might not have existed anywhere in the galaxy. Earth wouldn't exist for another 6 or 7 billion years. The sun wouldn't ignite for the same span, but other worlds might have been inhabited. Other civilizations might have risen. This is where the Drake equation becomes relevant, the mathematical framework for estimating how many intelligent civilizations might exist in the galaxy. The equation considers factors like star formation rates, the fraction of stars with planets, the fraction of those planets that develop life, and so on. When you plug in numbers for conditions 11 billion years ago, something interesting emerges. There was time. Plenty of time for life to arise, evolve intelligence, develop technology, and either thrive or die out long before our solar system formed. The Fermi paradox asks, if intelligent life is common, where is everybody? Why haven't we seen evidence of other civilizations? One answer: we're looking at the wrong timescale. If civilizations rise and fall over millions of years and the galaxy is billions of years old, then most intelligent species might be long extinct by now. Their signals have faded, their artifacts have decayed or been destroyed by cosmic processes, except for the things they made durable, except for the things designed to survive. If you wanted to send a message across cosmic time, a message that would persist for billions of years, what would you make it from? Not radio waves. Those dissipate with distance and time. Not spacecraft with active systems. Those require energy maintenance and eventually fail, but a physical object. Dense. Chemically stable. Designed to endure the harsh environment of interstellar space. An object that could travel through the galaxy for billions of years, passing stellar system after stellar system, waiting. This is speculation, but it's speculation grounded in a real question. What would a message from deep time look like? Maybe it would look exactly like what 3I Atlas appears to be. Old, durable, composed of materials that resist weathering, following a trajectory that brings it through the habitable zones of star systems it encounters, and displaying anomalies. Behaviors that don't quite fit natural patterns, just enough strangeness to make observers pay attention. The ancient Egyptians understood deep time in their own way. Their civilization lasted 3,000 years, an extraordinary span by human standards. They built monuments designed to endure, pyramids, temples, obelisks carved from granite and limestone. They did this because they wanted to send messages to the future. They wanted their names, their achievements, their beliefs to persist beyond their lifetimes. And it worked. We can read their hieroglyphs, we can walk through their temples, we can stand in the burial chambers they constructed and feel the weight of that intentional persistence. 3I Atlas has persisted longer than any human monument, longer than our species has existed, longer than our planet has been habitable. It has survived cosmic radiation that would erode ordinary materials, micrometeorite impacts that would fragment softer objects, Temperature extremes, cycling between near absolute zero in the voids between stars and potential hundreds of degrees when passing near other suns. And now it's here passing through our solar system, carrying information about conditions and compositions from an era we can only infer through mathematics and spectroscopy. Whether it's a natural cosmic fossil or something more, that question remains open. But either way, it's a window into deep time. A messenger from the ancient galaxy speaking in the language of chemistry and physics, telling us about origins we'll never directly observe. The ammonite fossil in the British Museum has a spiral pattern that follows mathematical principles, the golden ratio logarithmic growth curves. Nature creates these patterns through simple rules, applied repeatedly over time. 3i Atlas has patterns too. Not in its shape, we can't resolve it well enough to see that, but in its behavior, its composition, its trajectory.
Are those patterns natural products of physics and chemistry operating over billions of years? Or do they contain information? Data encoded in isotope ratios, trajectory choices, material compositions. A message written not in radio waves or binary code, but in the fundamental properties of matter. We're reading the fossil, analyzing it, trying to extract meaning, but we may not have the framework yet to understand what it's telling us, just as someone who didn't know what an ammonite was might look at that fossil and see only a pretty spiral stone. We might be looking at 3i Atlas and seeing only a strange comet, missing the deeper message preserved in its ancient structure. High on the Giza Plateau within the Great Pyramid, there are two narrow shafts that extend from the king's chamber toward the pyramid's exterior. They're not passageways, they're too small for that. They're precisely angled channels cut with extraordinary accuracy through the massive limestone blocks. For years, Egyptologists debated their purpose: ventilation, symbolic passages for the pharaoh's spirit. Then, in the 1960s, astronomer Virginia Trimble calculated where these shafts pointed relative to the sky when the pyramid was built around 2560 BCE. The southern shaft aligned with Al-Nitak, the brightest star in Orion's belt, associated with Osiris, god of the afterlife and rebirth. The northern shaft pointed toward the circumpolar stars that never set, eternally circling the celestial pole, representing immortality. These weren't random. They were deliberate astronomical alignments built into a structure that took decades to construct and used materials transported hundreds of miles. The ancient Egyptians were watching the sky with profound attention and encoding that attention into their most sacred monuments. They weren't alone. The Maya built observatories like El Caracol at Chichen Itza, with windows aligned to track Venus's position at key points in its cycle. They calculated Venus's synodic period, the time between one maximum elongation and the next, to within minutes of the actual value, using only naked eye observations over centuries. The Sumerians in ancient Mesopotamia kept detailed astronomical records on clay tablets, documenting planetary positions, lunar eclipses, cometary appearances. Their records were so precise that modern astronomers use them to calculate long-term orbital perturbations and refine historical timelines. The Antikythera mechanism, recovered from a shipwreck off the Greek coast and dated to around 100 BCE, is a mechanical computer of stunning sophistication. It used bronze gears and dials to predict astronomical positions decades in advance, eclipses, planetary locations, Olympic Games schedules tied to lunar cycles. These ancient astronomers didn't have telescopes. They didn't have photography or spectroscopy. They couldn't measure distances to stars or calculate orbital velocities. But they had something we've lost in our data-saturated age: time and attention. They watched the sky every night for generations. They noticed patterns. They recorded changes. They treated celestial phenomena as worthy of preservation and transmission across centuries. And they specifically noted unusual events: comets, bright stars that appeared suddenly, objects that moved in unexpected ways. These were omens, yes, messages from gods.
but they were also data points, observations that didn't fit the regular patterns of sun, moon, and planets. Did they ever observe interstellar visitors? Almost certainly. Oumuamua, 2I Borisov, and 3I Atlas are only the ones we've detected in the past 8 years using modern technology. Statistical modeling suggests interstellar objects pass through the inner solar system far more often, perhaps several per year. Most would be too faint to see without telescopes, but occasionally one would be close enough, large enough, bright enough to be visible to the naked eye. Ancient observers would have seen it as a comet. They wouldn't know it came from another star system. That distinction requires orbital calculations beyond their mathematics, but they would notice if it behaved strangely, if it moved differently than known comets, if its tail pointed the wrong direction, if it brightened unexpectedly, and they would record it. Somewhere in the archives of lost texts, the Library of Alexandria, before it burned the Maya codices destroyed by Spanish conquistadors, the countless clay tablets still buried in Mesopotamian ruins, there might be descriptions of objects like 3I Atlas, comets that didn't follow the rules, visitors that came from the wrong direction, moved against expected patterns, displayed colors or behaviors that marked them as unusual. These descriptions would be wrapped in mythological language, interpreted through religious frameworks. But beneath the metaphor, there might be real observations of real phenomena. The Sumerians had a concept called Nibiru, a celestial body associated with the god Marduk. In some interpretations, Nibiru was a wandering planet that appeared periodically. In others, it was a star or comet with special significance. The texts describing Nibiru are fragmentary and debated, but they suggest an object that came from the deep, possibly meaning space beyond the known planets, that brought both destruction and renewal, and that marked transitions between cosmic ages. Does this describe an interstellar visitor? Possibly, or it might be pure mythology unconnected to any real astronomical event. We can't know. The evidence is too fragmentary, but here's what we can say with confidence. Ancient civilizations took sky watching seriously. They built monuments to mark celestial alignments. They devoted resources to tracking and predicting astronomical phenomena. They preserved these observations across generations, considering them important enough to encode in stone clay and carefully guarded oral traditions. They did this because they understood something fundamental: the universe speaks if you listen patiently enough. Modern astronomy has given us extraordinary tools. We can detect objects billions of light years away. We can analyze the chemistry of distant nebulae. We can watch galaxies collide and black holes merge. But we've lost something in the process: the willingness to sit with mystery. Ancient observers didn't need to immediately explain everything they saw. They could record an anomalous event, preserve the description, and trust that future generations might understand it better. They built monuments that ask questions rather than providing answers. The pyramids don't explain the cosmos, they point to it saying, "Look here, this matters. Remember this." 3I Atlas is doing the same thing in a sense. It's pointing, saying, "Look here, something unusual is happening. Remember this." Whether we have the wisdom to listen, whether we can resist the urge to force it into comfortable explanations, and instead sit with the uncertainty that remains to be seen. But the ancient astronomers would recognize this moment. They would see an object displaying 10 separate anomalies and understand this is significant. This deserves careful observation, meticulous recording, and transmission to future generations who might have better tools to understand it. They wouldn't dismiss it. They wouldn't force it into existing categories. They would watch, record, preserve, and perhaps in their monuments and texts, they would leave clues for us, descriptions of similar visitors from millennia past, waiting to be decoded by those willing to look beyond the literal words to the observations beneath. The stars are still speaking. We just need to remember how to listen. Flip a coin once. You get heads or tails. 50-50 chance. Nothing remarkable. Flip it twice. If you get heads both times, that's a 1 in 4 outcome, still pretty common. Flip it 10 times and get heads every single time. Now you're at 1 in 1,024. Possible but unusual enough that you might start suspecting the coin is weighted. This is the probability cascade. Each unlikely event compounded with others multiplies into vanishingly small odds. 3i Atlas presents us with 10 documented anomalies, 10 separate coin flips each coming up heads. Let's review them. Anomaly 1, ecliptic alignment. Trajectory within 5 degrees of the solar system's planetary plane. Probability 0.2%. Anomaly. 2 planetary encounter sequence. Path bringing it past Venus, Mars, and Jupiter while spacecraft were positioned to observe. Probability 0.005%. Anomaly. 3 mass and velocity combination. Exceptionally large and fast compared to other interstellar objects. Probability 0.1%. Anomaly 4. Chemical composition. More nickel than iron, orders of magnitude more nickel relative to cyanide than any known comet. Probability below 1%. Anomaly 5. Low water content. Only 4% water despite showing cometary activity. Probability below 1%. Anomaly 6. Sunward jet. Material ejecting toward the sun against radiation pressure. No known natural mechanism. Probability unmeasurable but effectively 0 for natural processes. Anomaly 7. Extreme brightness surge. Brightening rate exceeding all database models. Probability below 1%. Anomaly 8. Blue coloration. Appearing bluer than the sun with no conventional explanation. Probability below 1%. Anomaly 9. Wow signal alignment. Arriving from within 9 degrees of the only unexplained artificial-looking radio signal ever detected. Probability 0.6%. Anomaly 10. Missing tail despite massive mass loss. 4 billion tons ejected but no visible tail. Probability below 1%. Now if these anomalies were independent, if one didn't affect the others, you'd multiply the probabilities. 0.2% times 0.005% times 0.1%. The result is staggeringly small. Far less than 1 in a million, possibly less than 1 in 10 million. But are they truly independent? This is where statistical analysis becomes tricky. Some anomalies might be related. For instance, the unusual composition could explain the low water content. If the object formed in an exotic environment, both characteristics might stem from that single unusual origin. The sunward jet and missing tail might be connected. If there's a non-standard outgassing mechanism at work, it could affect both observations. So we can't simply multiply all the probabilities and claim the result is definitive. That would be statistically naive. But even if we're generous, even if we assume half the anomalies are correlated and not truly independent, the cumulative probability remains extremely small. 1 in 10,000. Perhaps 1 in 100,000. That's the chance that all these unusual characteristics would appear together in the same object purely by random coincidence. This is where Bayesian reasoning becomes useful. Bayesian analysis doesn't ask, what is the probability of hypothesis X being true? Instead, it asks, given these observations, how should I update my confidence in different hypotheses? Start with prior probabilities, your best guess before seeing new evidence. Prior for natural origin, very high, maybe 99%. Most objects in space are natural. We've observed billions of celestial bodies, and all but a handful have natural explanations. Prior for artificial origin, very low, maybe 1% or less. We've never confirmed an artificial object from outside our solar system. Now update based on evidence. Each anomaly shifts the probabilities. Natural origin becomes slightly less likely. Artificial origin becomes slightly more likely. After 1 or 2 anomalies, natural origin still dominates. The shift is minor. After 5 anomalies, the confidence in purely natural explanations starts weakening. After 10 anomalies with cumulative probability below 1 in 10,000, the Bayesian update becomes substantial, not enough to definitively prove artificial origin. The prior for that hypothesis was so low that you'd need even more extreme evidence, but enough to shift the conversation from almost certainly natural to uncertain requires further investigation. This is precisely what Harvard astrophysicist Avi Loeb has been arguing. Loeb isn't claiming 3I Atlas is definitely artificial. He's claiming the evidence is sufficiently unusual that we should seriously investigate the possibility rather than dismissing it out of hand. And he's facing criticism for it. Colleagues accuse him of sensationalism, of damaging the public's understanding of science by entertaining exotic explanations. But Loeb's response is simple. The data is what the data is. If 10 independent anomalies appear in the same object, that's not sensationalism. That's observation. And if we're not willing to follow evidence wherever it leads, even to uncomfortable conclusions, then we're not doing science. We're protecting dogma. Historically, science has advanced precisely when someone was willing to question consensus. When Galileo looked through his telescope and saw moons orbiting Jupiter, the scientific consensus based on Aristotelian physics said this was impossible. Everything orbited Earth. Galileo said, "Look through the telescope, see for yourself." When Alfred Wegener proposed continental drift in 1912, the geological consensus rejected it. Continents couldn't move. The idea was absurd. Wegener said, "Look at the evidence, matching fossils across oceans, puzzle piece coastlines, rock formations that line up." He was ridiculed during his lifetime, died without seeing his theory accepted. Decades later, plate tectonics, the mechanism underlying continental drift, was confirmed through seafloor mapping and became the foundation of modern geology. When Jocelyn Bell detected the first pulsar signal in 1967, a radio source pulsing with extraordinary regularity, she and her advisor considered whether it might be artificial. An alien beacon, they called it LGM-1, Little Green Men 1. After detecting more pulsars and understanding their characteristics, they realized these were natural phenomena neutron stars with powerful magnetic fields rotating rapidly and beaming radio waves like cosmic lighthouses. But they didn't dismiss the artificial hypothesis immediately. They investigated, they gathered more data, they let evidence determine the conclusion. That's good science. Loeb is advocating for the same approach with 3I Atlas. Don't dismiss. Don't jump to conclusions. Investigate, gather data, let evidence guide interpretation. The probability cascade tells us something definitive. All 10 anomalies appearing together in the same object by pure chance is extremely unlikely. What that means, whether it points to exotic natural phenomena we don't understand or to something genuinely artificial, remains uncertain. But the first step is acknowledging the improbability, not explaining it away with stacked special circumstances, but honestly confronting the fact that we're seeing something rare, something at the far tail of statistical distributions, something that demands attention and careful analysis. Ancient astronomers understood this intuitively. When they saw something unusual, they didn't force it into comfortable categories. They marked it as significant. They called it an omen, not because they believed gods were directly intervening, but because rare events might contain information, might signal changes, or reveal previously hidden patterns. The probability cascade is our mathematical version of recognizing omens. It's our way of saying, this is not typical. This requires explanation. And until we have that explanation, the mystery remains. 10 coin flips. 10 heads. Either we're witnessing extraordinary coincidence, or the coin is weighted. There's a thought experiment called the cosmic archaeology scenario proposed by various scientists over the years, but most famously associated with Freeman Dyson and Carl Sagan. It goes like this. Imagine an advanced civilization arises billions of years before humans. They develop technology, explore their star system, perhaps even begin exploring neighboring systems. Eventually, like all biological species, they go extinct. Maybe catastrophic war, maybe environmental collapse, maybe simply the natural life cycle of intelligent life, a million years of existence followed by disappearance. But their artifacts remain. Probes sent into space, structures built on airless moons, objects designed to persist long after their creators are gone. These artifacts drift through the galaxy for billions of years. Most are destroyed by collisions or decay. But a few, the most durable, the best designed, survive. And occasionally they pass through star systems like ours. If you encountered one of these ancient artifacts, what would it look like? Not a gleaming spacecraft with visible engines and antenna. Billions of years of micrometeorite impacts and radiation exposure would erode surface features. It would be pitted, darkened, weathered. Not an object broadcasting radio signals. Any power source would be exhausted. Solar panels degraded. Batteries long dead. It would be silent, inert, indistinguishable at first glance from a natural asteroid or comet, except for subtle clues. Anomalies in composition, perhaps materials chosen for durability rather than cosmic abundance. Anomalies in trajectory may be remnants of ancient course corrections now frozen into its orbital parameters. Anomalies in structure or behavior that don't quite match natural processes. This is what cosmic archaeologists would look for, not obvious machines, but subtle deviations from natural patterns that suggest design, intention, purpose. The question with 3i Atlas is whether its anomalies constitute such deviations. Let's be clear about the burden of proof. Extraordinary claims require extraordinary evidence. Claiming an interstellar object is artificial would be extraordinary. Therefore, the evidence bar is high. What would constitute proof? Definitive markers of artificiality might include non-random surface patterns, visible at high-resolution geometric shapes, regular structures, repeated motifs that couldn't form naturally, anomalous acceleration that can't be explained by outgassing or radiation pressure suggesting active propulsion or trajectory control. Radio or other electromagnetic emissions with characteristics indicating technology, narrow band signals, modulation patterns, information content. Chemical composition that includes manufactured compounds, isotope ratios inconsistent with natural nucleosynthesis or structural materials assembled in ways nature doesn't produce. None of these have been definitively detected in 3i Atlas. The images from Tianwen-1 don't have enough resolution to show surface details. We see a fuzzy sphere, not a structured object. The non-gravitational acceleration, while unusual in its lack of a visible tail, can potentially be explained by pure gas ejection or other natural mechanisms. No radio emissions have been reported. If the object ever broadcast, it's silent now. The chemical composition is unusual but not impossible for natural formation under exotic conditions, so we don't have proof of artificiality. But we have enough anomalies to warrant asking the question seriously. This is where Avi Loeb's advocacy becomes important. He's not claiming he's proven 3i Atlas is artificial. He's claiming that given the evidence, the possibility should be investigated rather than dismissed. And this advocacy has generated fierce debate. Many scientists argue that entertaining the artificial hypothesis without definitive evidence is irresponsible. It encourages speculation, generates misleading headlines, and damages public understanding of how science works. They point to history, countless claims of UFOs, alien structures on Mars, signals from extraterrestrials, all eventually explained by natural phenomena, instrumental artifacts, or misidentification. Why should 3i Atlas be different? Loeb's response centers on the Copernican principle. Earth and humanity are not special. We exist in a typical star system, in a typical galaxy, at a typical time in cosmic history. If we're typical, then intelligence arising on other planets should also be typical. And if intelligence is typical, then across billions of years and trillions of stars, technological artifacts should exist in the galaxy. The question isn't whether such artifacts exist. The question is whether we've encountered one. And to answer that, we need to look carefully, without premature dismissal, but also without premature acceptance. The von Neumann probe concept is relevant here. Mathematician John von Neumann proposed that a sufficiently advanced civilization could build self-replicating probes, machines that travel to other star systems, gather resources, build copies of themselves, and send those copies onward. Over millions of years, such probes could spread throughout the galaxy, exponentially visiting every star system multiple times. If such probes exist, we should eventually encounter one. Would we recognize it? That depends on its design. If it's actively operating, broadcasting, moving with obvious propulsion, yes, probably. But if it's ancient, dormant, or designed for passive observation, it might look exactly like a natural object, with just enough anomalies to make us wonder. Ancient philosophers understood the challenge of recognizing design in nature. The Greek philosopher Anaxagoras in the 5th century BCE proposed that life's origin came from seeds spread throughout the cosmos. Panspermia, the idea that life's building blocks or even life itself traveled between worlds. This wasn't mysticism, it was reasoning based on observations of meteorites and celestial phenomena. If rocks fell from space, why not seeds? Why not information? Modern panspermia theories now discussed seriously in scientific literature suggest similar ideas. Organic molecules do exist in space. Meteorites have delivered amino acids to Earth. Life's origin might involve extraterrestrial material. But what if panspermia wasn't accidental? What if someone billions of years ago deliberately spread life throughout the galaxy? What if objects like 3I Atlas aren't just wandering debris, but part of a long-forgotten galactic gardening project, seeding worlds with the raw materials for life? This is speculation, highly speculative, but it illustrates the difficulty of the question we're facing. When you encounter something with characteristics that don't quite fit natural processes, at what point do you seriously consider designed origin? The answer can't be never. That would be intellectually closed-minded. But it also can't be immediately. That would be scientifically irresponsible. The sweet spot is somewhere in between serious investigation, careful analysis, willingness to follow evidence, and intellectual humility about what we don't know. 3I Atlas, with its 10 anomalies and improbable cascade of unusual characteristics, has earned that serious investigation. Not sensational headlines, not premature conclusions, but genuine scientific attention without dismissive hand-waving or forcing data into comfortable categories. Whether it turns out to be a natural object with an exotic formation history or something more profound, we won't know until we're willing to look honestly at all possibilities. And that requires courage, the courage to ask uncomfortable questions even when the answers might challenge our understanding of our place in the cosmos. There's a photograph from 1972 called The Blue Marble. It shows Earth from space, photographed by the Apollo 17 crew on their way to the moon. The whole planet in one frame, swirling white clouds, deep blue oceans, brown and green continents. That image changed how humanity sees itself. It showed our world as finite, beautiful, fragile, a tiny island in the vastness of space. The images from Tianwen-1 might eventually hold similar significance, though in a different way. They're not beautiful, they're not even particularly clear. They show a fuzzy sphere of light against darkness, barely resolved, grainy from distance and sensor limitations. But they represent something profound, humanity's closest look at an object from another star system. A visitor from interstellar space photographed from just 18 million miles away. For context, that's approximately 1/5 the distance from Earth to the Sun. In cosmic terms, that's remarkably close. Hubble Space Telescope observed 3 Atlas from Earth orbit. Its images taken in July 2025 showed the object as a tiny smudge with some coma structure. James Webb Space Telescope also turned its infrared gaze toward the comet, capturing data about its thermal emission and composition. Those results added to the growing body of spectroscopic evidence about the object's unusual chemistry. But Tianwen-1's images are different. Not because of resolution. Hubble and Webb probably captured sharper details, but because of proximity. Tianwen-1 was there, at Mars, closer to the object than any Earth-based or Earth-orbiting observatory could get, and that proximity matters. Light from 3I Atlas took 1 minute to reach Tianwen-1's camera. By comparison, light from the same object took about 15 minutes to reach Earth. That 1-minute light travel time represents connection, immediacy. Tianwen-1 was sharing the same local environment as this ancient visitor, both moving through the solar system together, briefly neighbors in the cosmic void. The Chinese National Space Administration's decision to attempt these observations was not guaranteed. Tianwen-1's primary mission was Mars science, studying the planet's geology, atmosphere, climate. Reorienting the spacecraft to track an interstellar object required complex calculations, precise timing, and acceptance that the observations might fail. The high-resolution camera was designed for bright planetary surfaces. Adapting it to photograph an object 10,000 times dimmer, moving at 58 kilometers per second, required pushing the instrument beyond its intended parameters. They succeeded, and what they captured will be studied for decades, because those images, however imperfect, contain information. The coma's structure, how light is distributed around the nucleus, reveals details about the outgassing pattern and particle size distribution. The lack of an obvious tail, that absence, is itself data telling us something about the nature of the ejected material or how it's being dispersed. The object's brightness in the images compared to known reference stars in the field provides photometric data that helps constrain its size and reflectivity. Every pixel contains clues, but there's something else. Those images represent timing. 3I Atlas was observable from Mars for only a brief window. Earlier, and it would have been too far away. Later, and it would have moved beyond useful range. Tianwen-1 captured it at the optimal moment, the closest approach, the best geometry, the ideal conditions for observation. That window will never open again. By the time you hear these words, 3I Atlas is already millions of miles farther from the Sun than it was when Tianwen-1 photographed it, moving outward at 200,000 kilometers per hour, leaving the inner solar system behind. NASA's Mars Reconnaissance Orbiter also observed the comet during its approach to Mars. Its high-rise camera, capable of even higher resolution than Tianwen-1's instrument, captured images on October 3rd. But those images haven't been released. During the government shutdown that began in late October 2025, NASA operations were affected. Data transmission continued, but processing and public release were delayed. Representative Anna Paulina Luna sent a letter to NASA's interim administrator urging release of the high-rise images. She argued that the information was of great scientific value and public interest shouldn't be held hostage to bureaucratic delays. As of early November, those images remained unreleased. So, Tianwen-1's photographs, published by the Chinese National Space Administration on November 5th, became the highest resolution publicly available images of 3I Atlas from its close approach to Mars. China, in this case, provided the world with data that American systems captured but didn't share. There's a lesson in that about scientific cooperation and the importance of multiple nations maintaining independent space capabilities. If only one country had Mars orbiters, and if political or bureaucratic issues prevented data release, humanity would have missed this opportunity entirely. But because multiple space agencies, Chinese, American, European, all had spacecraft positioned to observe the data, got out. The images themselves will become historical artifacts, not beautiful photographs suitable for framing, but important scientific documents. Evidence of humanity's first detailed encounter with an interstellar visitor during the early era of space exploration. Future historians will look back at November 2025 the way we look back at Galileo's first telescopic observations of Jupiter's moons in 1610. Not because the images themselves are technically impressive, they're not by any absolute standard, but because they represent a threshold crossed. A moment when something previously theoretical became observable, measurable, real. Interstellar objects were hypothetical until 2017. We knew they must exist, galactic dynamics demanded it, but we'd never seen one. Now, 8 years later, we have close-up photographs from Mars' orbit. We have spectroscopic data. We have trajectory calculations and compositional analyses. We're building a database, a catalog of visitors from other stars. And 3i Atlas, with all its anomalies and mysteries, will be a cornerstone of that catalog. The object that showed us how much we still don't understand. The object that pushed our observational capabilities to their limits and revealed patterns that don't quite fit our models. The object that, whether natural or otherwise, demanded we take interstellar astronomy seriously. Tianwen-1's images are the proof. The evidence that we were paying attention when something extraordinary passed through our neighborhood. And when 3i Atlas exits the solar system in January 2026, those images will be all we have left. Pixels preserving light that traveled from an ancient object reflected off its surface crossed 18 million miles of space and was captured by human technology orbiting a world we've only recently begun to explore. It's a chain of connections stretching from the distant past to the near future, linking disparate times and places through the simple act of observation. The ancient astronomers who built Stonehenge, who carved celestial maps in caves, who recorded planetary positions on clay tablets, they understood this. Observation is memory. Documentation is defiance against forgetting. Tianwen-1's images ensure that whatever 3i Atlas is, whatever it represents, it won't be forgotten. Right now, as you hear these words, 3i Atlas is leaving. It's approximately 400 million kilometers from the Sun, somewhere between the orbits of Mars and Jupiter, moving outward at more than 200,000 kilometers per hour. That's 55 kilometers every second. In the time it takes you to draw a single breath, the object travels 200 kilometers farther from the Sun. By December 19, 2025, it will make its final close approach to Earth, passing about 270 million kilometers away. That's roughly 700 times the distance to the Moon. For a few days around that date, the most powerful telescopes on Earth will have one last opportunity to observe it before it fades beyond detection limits. Some telescopes will attempt spectroscopy, trying to capture one final chemical signature as the object's activity diminishes with increasing distance from the Sun. Others will focus on photometry, measuring how its brightness changes to infer rotation rates and surface properties. A few will simply photograph it, documenting its position against the background stars, adding to the astrometric data that defines its trajectory. And then it will be gone. By January 2026, 3i Atlas will cross the boundary we informally define as the edge of the solar system, beyond Neptune's orbit, beyond the Kuiper belt, into the scattered disk where sunlight becomes too weak to significantly heat objects. Its activity will cease. No more outgassing, no more coma, just a frozen nucleus, dark and cold, becoming invisible even to our best instruments. It will continue outward, beyond Pluto's orbit, beyond the detached objects like Sedna and Eris, into the Oort cloud, that vast spherical shell of icy bodies surrounding our solar system at distances up to a light year from the Sun. And then beyond, even that, into true interstellar space. The journey back will take millions of years. At its current velocity, 3i Atlas will travel about 1 light-year every 17,000 years. The nearest star system to our own Alpha Centauri is roughly 4 light-years away. The object won't pass particularly close to that system, but even if it did, the journey would take 70,000 years. It will continue drifting through the Orion spur of the Milky Way, occasionally perturbed by gravitational encounters with other stars, but generally following its trajectory outward through the galaxy. Where is it going? Nowhere specific. Objects in interstellar space don't have destinations. They have trajectories paths determined by velocity and gravitational influences extending indefinitely until something changes them. 3I Atlas will pass through regions of space where starlight is dim, where temperatures approach absolute zero, where matter is so sparse that a cubic meter might contain only a few atoms. It will pass through denser regions, 2 molecular clouds, where new stars are forming stellar nurseries, glowing with the light of protostars. It might pass near other planetary systems, close enough that hypothetical observers there could detect it, measure it, wonder about it. And eventually, billions of years from now, its journey will end. A collision with another object, perhaps. Gravitational capture by a star or black hole. Gradual erosion by radiation and impacts until nothing recognizable remains. But that's far in the future. For now, it's simply leaving, and we're watching it go. There's a bitter sweetness to this. We barely had time to understand it. From first detection in July 2025 to exit from the inner solar system in January 2026, just 6 months. 6 months to observe, analyze, debate, and form hypotheses about an object that traveled for potentially billions of years to reach us. It's like meeting someone fascinating at a train station. You have time for one conversation, maybe an hour before their train departs. You ask questions, exchange stories, make connections, and then they're gone, off to their next destination, carrying their mysteries with them. You're left with memories, notes from the conversation, questions you wish you'd asked, insights you gained too late to follow up on. That's where we are with 3I Atlas. We have data, we have images, we have spectroscopic analyses and trajectory calculations. But we also have unanswered questions. 10 documented anomalies, each one requiring explanation. Chemical compositions that don't match known comets. A missing tail despite massive mass loss, brightness changes and color shifts that defy conventional models. We have pieces of a puzzle, but we don't know what the final picture looks like. Maybe future observations of other interstellar objects will provide context. Maybe when we've detected 50 or 100 visitors from other star systems, patterns will emerge. We'll understand what's typical and what's anomalous. We'll develop better models for how objects behave when they've been wandering the galaxy for billions of years. Or maybe 3I Atlas will remain unique, an outlier, the one that didn't fit any pattern, that challenged every assumption, that left more questions than answers. Either way, its departure marks an ending, the closure of a brief window when humanity and an ancient traveler shared the same cosmic neighborhood. Think about what that means. This object might have formed 11 billion years ago. It has existed for more than twice as long as our entire solar system. It has seen, if an inanimate object can be said to see, things we can only imagine. The births and deaths of stars, the collision of galaxies, the slow evolution of the Milky Way from a chaotic star-forming maelstrom to the more mature spiral we inhabit today. It has passed through regions of space where no human will ever travel, where no human instrument will ever reach, carrying information about those places encoded in its composition, its structure, its history of impacts and radiation exposure. And for 6 months it was here, in our system, close enough to photograph, close enough to analyze. Now it's leaving, taking that information with it back into the darkness. We extracted what we could, but there's so much more we would have learned with more time, better instruments, closer approaches. If only it had passed within the orbit of Mars instead of outside it. If only we'd had a spacecraft positioned along its trajectory, capable of matching velocity and conducting a rendezvous. If only our detection systems had spotted it years earlier, giving us time to plan a dedicated mission. If only. But space exploration doesn't work that way. We get the opportunities we get under the conditions that exist at the time. We make do with Mars orbiters designed for planetary science. We adapt telescopes built for other purposes. We extract every bit of data possible from instruments pushed beyond their design parameters, and we accept that some questions will remain unanswered. The ancient astronomers understood this better than we do, perhaps. They watched celestial events knowing they were unrepeatable. A comet appears, graces the sky for weeks or months, and vanishes. Gone forever. You either observe it during that window or you miss it entirely. They didn't have the luxury of recordings, of data archives, of reviewing observations months or years later. They had to pay attention in the moment, record what they could, and then let the event pass into memory and history. We have better technology, but the fundamental constraint remains the same. 3i Atlas gave us one chance. We took it, we documented what we could, and now it's leaving. By the time a child born today is old enough to attend school, 3i Atlas will be beyond Neptune, invisible to all our telescopes, utterly lost to human observation. By the time that child graduates from university, the object will be light years away, continuing its eternal wandering through the galaxy. And by the time that child reaches old age, 3i Atlas will be so distant that even its trajectory becomes uncertain. Small perturbations from distant stars will have nudged it onto slightly different paths and will have lost track entirely. It will become a legend. The third interstellar visitor, the anomalous one, the object that displayed 10 separate violations of expected behavior and then vanished before we could fully understand it. Future astronomers will read about it in historical accounts. They'll study the data we collected, analyze the images Tianwen-1 captured, debate the interpretations we proposed. Maybe they'll have better theories. Maybe advances in astrophysics, chemistry, or planetary science will provide explanations we couldn't conceive in 2025. Or maybe the mystery will persist. Maybe 3i Atlas will remain an unsolved puzzle, a reminder that the universe contains phenomena we don't yet have frameworks to understand. Either way, its departure marks an ending, but also a beginning, because 3i Atlas taught us what to look for. It showed us that interstellar objects can be far stranger than we anticipated. It revealed gaps in our understanding, challenged our models, and forced us to consider possibilities we dismissed as unlikely. The next interstellar visitor will be met with better preparation. We'll have more sensitive detection systems. We'll have contingency plans for rapid observation campaigns. We'll have a growing database of previous visitors to compare against. And maybe, just maybe, we'll be ready to recognize something truly extraordinary if it arrives. Because one thing is certain, more are coming. The galaxy is vast, billions of stars, trillions of planetary systems. Countless opportunities for objects to be ejected into interstellar space through gravitational interactions, collisions, stellar evolution. Some tiny fraction of those objects pass through our solar system. We're detecting them now because our technology has finally reached the threshold where they're observable. In 10 years, we might have detected 20 interstellar objects. In 20 years, 50. In a century, thousands. Each one a messenger from elsewhere, each one carrying information about conditions, chemistry, and processes we can't study any other way. Each one a cosmic postcard from distant star systems we'll never visit. 3i Atlas was the third postcard. Strange. Cryptic, covered in stamps we can't quite read. But undeniably real. Undeniably here, however, briefly. And now undeniably leaving. So we watch it go, we preserve the data, we continue the analysis, we write papers and debate interpretations and build better models. And we wait for the next arrival, because the universe is telling us something through these visitors. Not a simple message, not an obvious signal, but something more subtle, a pattern emerging from multiple data points, each one adding to our understanding of what exists beyond our solar system's boundaries. 3i Atlas was one piece of that pattern, a crucial piece because it showed us the edges, the extremes of what interstellar objects can be. The next piece might be more conventional, or it might be even stranger. We won't know until it arrives, but we'll be watching, always watching, because that's what we do. That's what humans have done since we first looked up at the night sky and wondered what those lights meant. We watch, we record, we try to understand, and sometimes when we're very lucky and very attentive, we catch a glimpse of something extraordinary, something from beyond, something that reminds us how vast and strange and wonderful the cosmos really is. 3i Atlas was that something,
and now it's returning to the darkness from which it came. Farewell, ancient traveler. May your journey continue for another billion years, and may the next civilization you encounter be wise enough to recognize you for what you are. We stand at the edge of evening, looking up at stars that are themselves looking back through time, somewhere above us, invisible now even to our most powerful instruments. 3i Atlas continues its ancient journey. It has already traveled farther from the Sun than Mars, orbits racing outward at speeds that would carry you from Earth to Moon in less than 2 hours. By mid-January, it will cross the boundary we call the heliopause, the edge where the Sun's influence fades into the interstellar medium. It will return to the darkness it came from, the vast spaces between stars where it has spent most of its existence, and we will never know for certain what it was. 10 anomalies.
10 separate violations of patterns we've observed in thousands of comets over centuries of astronomy, each one explicable perhaps through special circumstances, unusual conditions, rare configurations, but all 10 together, all 10 in the same object at the same time. The mathematics whisper something uncomfortable. Either we've witnessed a statistical miracle, an event so unlikely it should happen perhaps once in 10,000 interstellar visitors, or we're missing something fundamental about this object's nature. Maybe it's natural but formed under conditions so exotic, so different from anything in our solar system that our models simply don't apply. Maybe it's revealing physics we haven't discovered yet, new mechanisms of cometary activity, new ways matter behaves under extreme conditions. Or maybe, and we must at least consider this, however uncomfortable it makes us, maybe it's something designed, something sent, something that followed that precise trajectory through our solar system, not by accident, but by ancient intention. Not a spacecraft in the way science fiction imagines, not a probe beaming back data to distant creators, but perhaps something simpler and stranger, a marker, a beacon, a bottle cast into the cosmic ocean billions of years ago, waiting for someone to notice. The ancient civilizations who watched the skies understood something we sometimes forget. Not everything that moves through the heavens needs to be explained immediately. Some mysteries are meant to endure, to provoke thought, to remind us how much we don't know. The Egyptians built monuments that asked questions. Why these alignments? Why these proportions? What did the builders know? The Maya calculated time with such precision that their calendar still makes us wonder, how did they achieve this without our technology? What were they really measuring? The Sumerians recorded celestial movements with devotion bordering on obsession. What were they searching for in those patterns? What message did they expect the sky to deliver? Maybe they were searching for exactly what we found in October 2025, something from beyond, something old, something that doesn't follow the rules. 3i Atlas will travel for millions more years. It will pass other stars, other systems, other worlds perhaps. Maybe one of those worlds hosts observers like us beings who look up at their sky and wonder. Maybe they'll detect it too, measure its composition, calculate its trajectory, note the same anomalies we noted. And maybe they'll ask the same questions. Is this natural or is this a message? We don't have the answer. Not yet. Perhaps not ever. But we have the question. And that ultimately is what distinguishes us from the endless silent objects that move through space, following gravity's commands without thought or wonder. We ask, we measure, we imagine. And sometimes when the universe presents something strange enough, we allow ourselves to consider possibilities that seem impossible until they're not. Here is the final question for you as 3i Atlas fades beyond our reach. If you could send a message into the darkness, a message that would travel for billions of years, passing through star systems unimaginable distances away, what would you want it to say? And if something already sent that message long ago, before your sun existed, before your world formed, shaped from materials forged in the cores of ancient stars,
Would you recognize it when it arrived? Would you see it as just another rock, another comet, another natural phenomenon to be catalogued and forgotten? Or would you notice the anomalies? The patterns that don't quite fit? The whispers of intention hidden in the language of physics and chemistry? Would you be brave enough to ask the uncomfortable question and patient enough to sit with not knowing the answer? The cosmos is patient. It has waited 13.8 billion years so far. It can wait a bit longer for us to understand. 3i Atlas gave us a glimpse, a momentary window into mysteries we're only beginning to appreciate. Maybe it was just a comet. Unusual, yes, but natural, formed in conditions we haven't encountered before, behaving in ways we haven't modeled yet, but ultimately explicable through physics and chemistry. Or maybe it was something more, something that changes our understanding not just of interstellar objects, but of our place in the cosmos, of whether we're alone, of what might be possible across the vast expanses of space and time. We don't know, but we're learning to ask better questions. And in the darkness above, invisible to our eyes but recorded forever in our data, an ancient traveler continues its journey, carrying secrets we couldn't quite unlock, leaving questions we'll ponder for generations, reminding us that the universe is stranger and more wonderful than we imagine, and that sometimes the most profound discoveries aren't the answers we find, but the questions we learn to ask.